Hello. So welcome to another section of Chapter 8. This will be 8.2. And I think generally this section should be pretty easy. There's maybe a few new ideas in it, but overall, generally, it's the sort of things um, well, you've kind of seen before, just maybe not for sequences. So, last time we had talked about sequences, and sequences were a list of numbers, right? Um, where we had kind of like something like this. So, say we have like 9, 4, -1, -6, -11, right? So it's like a list of numbers like this, okay? And so we typically kind of gave these our sequences a name. Um, Sometimes we call it a sub n, right? And so this was like a sub 1, that was the first term. This was a sub 2, this was a sub 3, a sub 4, and so on, right? A sub 5, right? So, in this case, the sequence that we're dealing with, we're going to be looking at a specific type of sequence today. And if you kind of look at this sequence and what's the pattern that's going on here, well, I start at 9, right? And then I go to 4. And so to get from 9 to 4, there's lots of ways you could do that. But then we also go, for the next one, we go from 4 to -1, right? So if you kind of notice the difference between these, right? To get from 9 to 4, you are subtracting 5, right? You would do 9 minus 5 would equal 4. Well, what happens to get from 4 to -1? What do you have to do? You also have to subtract 5, right? And to get from -1 to -6, you also subtract 5, and so on, okay? So you'll notice here, in this sequence, kind of the pattern is, for every one that you go, you subtract 5 from the previous number, right, to get the next number. And so if you kind of thought about this on a graph, what would this be? We don't have like the in-between places anymore, but like when n equals 1, so when n equals 1, we're at 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So we're up here. And then when n equals 2, we're at 4. So we go essentially down 5, right? 1, 2, 3, 4. Okay. And then when we're at n equals 3, we're at -1. Okay. And I haven't drawn this perfectly, but if I had, you'll notice that every time you're going down by the same amount, right? And so all of these points would be on a line, right? They'd be collinear with each other. Now, technically, the graph of this sequence wouldn't have the line actually filled in. It would just have the dots, but they would all be on a line, okay? And so this is an example of what is called an arithmetic sequence. Okay, so this is an arithmetic sequence, and it's basically the same as a linear function, okay? But for a sequence, right, we can only plug in the natural numbers. So it is a little different, but functionally, they have a constant rate of change. It's just for the sequence, we're not going to have the line filled in. We will just have dots on the line, right? And they'll all be you could draw a line connecting all of them, but the equation doesn't actually fill in all the dots on the on the in-between, because you can only plug in 1, 2, 3, 4, 5, 6, 7, 8 for n, right? You can't plug in any fractions or anything weird like that, okay? So essentially arithmetic sequences, those are really the same as your linear functions, okay, from before. They're just sequences, okay? So if you remember kind of the general form for an equation of a linear function, a linear function was, well, either f of x or y equals mx plus b, right? We had a constant rate of change, m. That was our slope. This is our slope. And then b was the y-intercept. Okay, so b was the y-intercept for our linear function. So we're going to do a very similar thing with this sequence that we have here. I want to be able to kind of generalize this for arithmetic sequences in a nice way so that I can write the equation for this arithmetic sequence. If you'll notice, every time we're going down by 5, so that would kind of be the same as m in this problem, okay? And our variable is going to be n, the term that you're on, sorry. And so let's maybe look at, with this sequence, how could I write a formula, the sequence that we're dealing with here, how could I write a formula for a sub n in terms of n, okay? Well, we'd kind of think, well, if it's similar to a linear function, it's going to be something like an, this is kind of like your y in that case, is equal to the slope or the rate of change. In the book, they call this d, okay? And then times n and plus b, okay? So that would be kind of what the equation would look like, okay? So let's kind of see how this works on our example. So here, we'll draw a line here. So for a sub n is dn plus b. Well, d is the difference between the terms of your sequence, okay? And so in this case, d is -5, right? Every time I'm going down 5, so it's going to be -5 times n, and then plus b, right? For the linear function, right, b was the y-intercept, okay? Well, right now, the y-intercept of this line is going to be happening over here, like up here, right? Because right now it's like here, it's going to put us up there. You may think initially that, oh, well, the very first thing in the the sequence is 9. So let's just put a 9 here because that's kind of where it starts out, right? And then it goes up, or it goes down 5 every time. The only issue is that if I do this, it is going to put my y-intercept at 9. So it would be like right here. It would give me a point right there. And I'm 9 not at 0, right? Not when n equals 0. I'm 9 at 1, right? So if I had done an equation like this, it would actually be a line more like this, okay? But notice, how are these two lines similar to each other? Well, if we draw, kind of fill them in, they're parallel to each other, right? And this one, this green point right here, is just, we have that right now, and we want to get this one, so I just really need to move it to the right one, okay? So in order to get the equation that I actually want, I just need to shift my green equation 1 to the right. And if you remember how we do that using using our transformations, we can just adjust our equation. We already said this equation doesn't quite work because 9 is not the y-intercept of this. But what will work is if we did a n is equal to -5. To shift to the right one, I subtract 1 from my variable n. So I throw in an n minus 1 and then plus 9. Okay, so, and we could check and see if this works. What happens when I plug in n equals 1 into here? Well, I get 1 minus 1 is 0 times -5 is 0 plus 9. So at 1, when I plug in 1 for this n, I get 9, just like we wanted to. If I plug in 2, I get 2 minus 1 is 1 times -5 is -5 plus 9 is 4. Okay, which is what I wanted to have happen. So this equation here, this an, is the equation for this sequence. You can plug in any n that you want and you will get out the nth term of the sequence, okay? And I know it looks a little bit weirder than the linear function. The main weirdness is just because this, right? It's because 9 is not actually the y-intercept of this sequence. You have to shift it to the right one, and so that's why this minus 1, that's where it's coming from, okay? So, in general, I'm going to kind of generalize this for an arithmetic sequence. There you go. Misspelling stuff. Arithmetic sequence. Okay. Our general form, kind of the general equation we're going to be dealing with, is an is equal to d, right, the common difference between terms, times n minus 1, because we got to shift it to the right one, so that because the first term is not the y-intercept, right? And then plus a, some number a, where a is just the first term of the sequence, okay? So I'll write that out. D is the common difference and a, this is the first term. So this is what the equations of arithmetic sequences normally look like, okay? they're like lines, and this is kind of the standard way we write the equations, okay? So I'm gonna just do an example. So example, so hopefully this will go kind of fast, but we've got an example. We want to find the first 5 terms of a sequence. We also want to find the common difference. And then lastly, we want a graph. Okay, of this sequence, and the sequence we're dealing with is a sub n is 1 plus 2 times n minus 1. Okay. Okay. So for A, we're looking for the first 5 terms of this sequence. So we just plug in the first 5 numbers. So we do 1. When we plug in 1, we get 1 plus 2 times 1 minus 1 is 0. So 0 times 2 is 0 plus 1 is 1. Okay. A2, we plug in 2 for n, right? We get 1 plus 2 times, well, 2 minus 1 is 1, times 2 is 2, plus 1 is 3. Okay. A3, we plug in 3, so we get 3 minus 1 is 2, times 2 is 4, plus 1 is 5. Just plugging those in. Okay, A4 is 4 minus 1 is 3, times 2 is 6, plus 1 is 7. And then lastly, A5 is 5 minus 1 is 4, times 2 is 8, plus 1 is 9. Okay, so that would be the first 5 terms of this sequence. 1, 3, 5, 7, 9. Okay. To find the common difference, you could either look at the terms here. How much are they changing? Well, to go from 1 to 3, you go up 2. And then to go from 3 to 5, you go up 2. Then from 5 to 7, you go up 2. Or you could just look at the equation. The common difference is what's in front of the n minus 1, right? So it's right here. That's your common difference. Okay, so d equals 2 in this case. Every time I'm going up by 2. Okay. The graph, let's get some more space here. The graph isn't too hard to do. It's essentially what you're used to doing for mx plus b, just a little bit. It's just shifted to the right. Okay. So, and we don't fill in the lines, right? So at A1 we're 1. Okay, and you can kind of see that here in the equation too, right? Whatever was out here was the first term. At 2, we're at 3. At 3, we're at 5. And then it just kind of continues off in that line with just dots. You don't, for sequences, you don't need to fill in the line between the points, because a sequence only happens at the whole numbers. Okay, so hopefully that kind of helps give you an idea of what arithmetic sequences are. They are exactly the same as linear functions. It's just, right, they're a sequence instead of a defined on any real number, right? So anyway, we'll do some more with arithmetic sequences and hopefully you'll get a good idea of how they work. I will see you in the next video.